This is the fourth video in this series based on our article, A Primer for Using Multilevel Models to Meta-Analyze Single Case Designs with A/B Phases, and it's published in the Journal of Applied Behavior Analysis. In this video, I'm going to show you how to use the effect sizes that I calculated in the third video to run a multi-level model in R. R is an open source and free statistical software program. It's completely syntax or code based, which means there's no drop-down menus, so you have to type everything in yourself. But it's very flexible and very powerful. We're using a specialty meta-analysis program called Medism, and this was developed by Mike Chung. So the very first thing we need to do after you open R is to download the Medism package. And we do that by typing in install.packages, and then the parentheses, and add a quotation mark, meta SEM. Make sure that you use the right case for this. R is case sensitive, so meta is lowercase, sem is in uppercase. Hit enter. It will ask you to select a secure crayon mirror. Doesn't really matter which you choose. Typically recommended to choose one that's close to you. So I'm going to pick the one in Tennessee since I'm in the United States. So you only need to install the package once, the very first time that you do this, and then from then on you don't have to do that step, and you only have to do this next step, which activates the package. So the next step is to activate it by typing library and then Medism, again being conscious of the case you're using. Hit enter. Next, we're going to read the data file that we prepared in video 3 that has all the effect sizes for each data set. The generic code is up here on the screen. First, we have to name the data set, and this can be anything that you choose. So I'm going to name mine because we're looking at spaced responding DRL. I'll name my data set SDRL. And it's good to keep it in lowercase since it is case sensitive, just makes it a little bit easier to do or type in. Equals read.csv. So anything in bold is really what we're changing here. The rest of that is generic code. Read CSV and then put the parentheses in. So I'm working on a Mac here, so to get my data path, I'm going to right click on my file and then click option. And then this copy as path name shows up. I can select that, come back over to R, put a quotation mark, and then paste it in. And then after the quotation mark, I'm going to add a comma and then put header equals T. That tells R that the first row are the variable names. And so then we can hit enter. And now the file is read into R. Next, we're going to run the multi-level model for the phase variable. So this will tell us the average effect of a DRL on behavior across all of the studies and all of our participants. And we use a 3-level model to test at level 1 the overall average effect, so across everybody, what's the average effect. At level 2, whether the effect varies across individuals within a study. And at level 3, whether that effect varies across studies. The generic code is as follows. So just like before, anything in bold is what we need to individualize. And I prefer really short model names, so I'm just going to call this S0 for spaced responding and the first model. So S0 equals meta 3, and then put the parentheses. Then we have to specify what Y is. So Y equals the effect size. And we called the effect size in our spreadsheet phase. So Y equals phase. V is the variance for that phase, and we call that V phase. Cluster is study. This allows the analysis to cluster participants within the same study. So that helps us determine at level 3 whether there's variation across studies. So cluster equals study. And then the data, so that's the data file that we read in, and I called that SDRL. We hit enter. enter. So we've run that model, but to get the results, we have to actually ask it for the results. And we do that by saying summary, and then typing in the model name, S sub 0, enter. And here's the output. So I'm going to walk you through some of the important results here. So if we go to, and I realize that this is not very pretty looking, but it has all the information we need. So we go to this first kind of grid of tables, and the first row is called the intercept. And this really is the main or average effect for level 1. And the first number under estimate, that tells us what that average effect is. So negative 7.1604, which is a statistically significant value. And I know that because this last column called PR, that is the significance level. So the p-value here is 0.001. All these columns in between tell us the value of the standard error and the confidence intervals and the test, which is a z-test. But what we're most interested in really is the estimate, the average effect, and the p-value. So this estimate, or this effect size here, can be interpreted as when we go from a baseline condition to a spaced responding DRL condition, on average across all of these people, there's about a 7 standard deviation change in behavior, and that change is negative, so that means it goes down. There's a reduction in behavior of 7 standard deviations. The next result I'm going to show you is the Q statistic. So this actually comes right after that table. And the Q statistic tests whether that effect size of negative 7 is uniform or if it's different across individuals and or studies. So a significant value here would indicate that the effect size is not the same across people. And our Q statistic is significant, so the bottom row p-value of the Q statistic, and it says it's 0, that means it's just so small that it doesn't even have an actual value. So there is significant variability. And given that, we can go back up to that first table where we see tau 2, and that tells us whether it's different across individuals or different across studies. So tau 2-2, the second row, that's level 2, and so that shows us across individuals. That is a significant value. Note that R uses the scientific number format, so the E minus 0.8 here means that we move the decimal 8 places to the left. So that's a really, really small p-value. So there's significant variability at level 2, but not at level 3. That value there is not significant. Consistent with tau, if we look at the heterogeneity indices, so this table here, it tells us the proportion of variation in the outcome that can be attributed to variability across individuals and variability across studies. And so most of the variation is coming from level 2. 0.83 is the proportion there, so we can interpret that as 83.86% of the variation comes from level 2, whereas only about 15% comes from level 3. So that's it. In the last video, I'm going to show you how to run the same model, but also including a moderator variable.